Hey curious kids, Kevin here. Welcome back to A Place Called Space. So we took a little break on Tuesday, but we're back here on Thursday, and we are going to start off this lesson with a question from a special guest, and I'm so excited for you to check out this video. So, let's have a look. Oh, hold on, let's try that again. There we go.
Hey kids, it's Matt Iseman, host of American Ninja Warrior, and welcome to A Place Called Space on YouTube, where you get all your questions answered by Kevin, the NASA rocket scientist, who, by the way, isn't just a rocket scientist, he's also an American Ninja Warrior. Now, I gotta tell you, personally, I think I became interested in space with Star Wars. I remember being a young kid, being in the theater and looking up at this galaxy far, far away, and just making me wonder what other worlds are out there. And Star Trek nurtured that in me too. The Next Generation was really mine. I'm a Captain Picard guy. So here's my question for Kevin, the rocket scientist. How fast can we travel in space right now? How fast can we go? Because I'm wondering, is warp speed real? Is light speed real? Can the Millennium Falcon do the Kessel Run in 12 parsecs? Well, what about maximum warp drive? So, Kevin, my question is this. How fast can we travel in space now? And how fast would we have to travel to go warp speed, to visit these other galaxies? What will the future hold in terms of speed in space? That's my question. Can't wait to hear your answer, Kevin.
Oh, baby Kevin came in there for a second. All right. Thank you, Matt. All right, so that's Matt Iseman, the host of American Ninja Warrior. So when I was competing on American Ninja Warrior, he's the one up in the booth commenting, telling me how I'm doing, and if I fall in the water, he'll make a joke. Well, so speed in space. How fast can we go? What's the future? And are these things he talked about, warp drive, light speed, are those real? What do they mean if you've never heard those words before? So let's talk about it. So we got speed, right? How fast things go. So if we're on Earth and we want to get into space, which is 100 kilometers, if you remember that, and we're going to take a rocket, which is how we get into space. So to get off of the surface of Earth, we got a rocket here, rockets there, rockets everywhere. We have to be going 17,500 miles per hour or 25,000 kilometers an hour. So we talked about that in previous episodes of, how do we get into space, how do rockets work, and all of that, like satellites. Which satellite? So the International Space Station over here is traveling around Earth at that 17,500 miles per hour. That's how fast you have to go to stay in orbit on Earth. So if we want to go out to these other galaxies, we're going to have to go faster than that because it's going to take a really long time. But how fast can we go? And how fast have we gone? Okay, so let's talk about it. We're going to bring up baby Kevin. Baby Kevin. Yeah. Okay. There's Kevin and Kevin. What's up? Now we got to make this one go away, and boom. There we are. All right, so you see the start screen over here. Got the Millennium Falcon here, so we'll take that. We'll move it over to the side for a second. All right, so we want to talk about speed in space. So we're talking about speed, and let's get up. I want to make sure I can, here we go, not too far. So to go into space, we have to be going, I'm going to use red. We have to be going 17,500 miles per hour. But you know me, like we're talking about space, right? So metric units, that's what we like to deal with. So that's 28,000. I might have said 25 before. I meant 28,000 kilometers per hour. All right. If you got questions, again, put them in the comment section so we can answer them and I can talk through them so that we know we're all learning at the same speed. Yeah, Glenn, it was super cool to be on ANW. That's American Ninja Warrior. We say ANW for short. Okay. Into space, 17,500 miles per hour or 28,000 kilometers an hour because we like to use the metric system. Okay, so we know that. So we're fighting against Earth's gravity, right? Gravity is what holds us down. So if I let go of Earth, what happens? It falls because gravity pulls it down. So gravity pulls us down at a certain rate, okay? So gravity. So gravity, here on Earth, it's a little bit different. Wes asked this question previously, is like the gravity of Earth changing, or is it going, it's getting smaller? So there's different parts on Earth that experience a little bit different gravity. Like at the equator is the most, and then it gets a little bit less towards the tops or towards places that are low, like valleys, have a little bit less gravity. But pretty much on average, it's really the same. You have to go like really, really, really small amounts to be different. So gravity is like 32, and I don't like this one, feet per second squared. But what we always use, is 9.8 meters per second squared. Okay, it's the metric units. So squared means this squared, that's just like a second times a second. It's a way that we figure out how fast things are going or how quickly something can go so fast. Okay, so that's what we need to talk about today, really, because we're talking about how fast can we go in space. So we got the 28,000 kilometers. We can go faster, right? We've gone that fast with the astronauts going to the International Space Station, right? On that SpaceX rocket. If you're here for the watch party on Saturday, they're up there hanging out. Update, they're going to be on the International Space Station for about 4 months, is what I hear. 4 months hanging out, and then they'll come back down to Earth. So we know that humans have gone that 17,500 miles per hour. And they've done it a lot because we've had so many people into space. So that's there. Now, we get the gravity. So we're fighting against gravity, and what we call that on Earth, the gravity, so equals 1 G. So one gravity on Earth, one force of gravity, is known as 1 G. So this is important, right? Because now we're going to talk about like roller coasters and planes and go into space. And we need to know what that G is. So let's get in here. So we got blue. Got to use blue. So I want to talk about speed. And then there's this word acceleration. Okay? Acceleration. So speed is how fast we're going at like a certain time, right? If we took like a picture, how fast are we going like in that picture, in that single moment? So it's how fast at a moment, I'll say. At a moment. We'll put in time. A moment in time. All right. Now acceleration, right, is how quickly we can speed up, right? So how long does it take you to go so fast? So if you're starting here at rest, hey Karem, thank you for tuning in. If you're sitting at rest, right, how long is it going to take you to go 100 miles an hour? So that time is called the acceleration. So if you can go 100 miles an hour in 1 hour, that means your acceleration is building up slowly, so in 1 hour you go that fast. So you don't automatically go that fast, right? Kind of slow up. You start going slow. So when you're in a car, like your mom or dad or your older brother or sister's driving, and they put their foot, you can't see me, but I'm moving my foot on the gas, you don't immediately like jump to 60 miles an hour on the freeway. You like slowly speed up, right? So that's acceleration. Acceleration is how fast you can speed up. Like how quickly, let's say. How quickly you can go fast. You can go fast. Because you start slow and then you start to go faster and faster and faster and faster. So what we experience here on Earth, so we just talked about gravity, right? That's 1 G. So we're always walking around on 1 G. So whenever you speed up, you're going a little bit faster than 1 G. And Jessica, hi, welcome. You've got a question here. Oh, Wes is here. So roller coasters go upside down. Why do they fall from gravity, or why do they not fall out from gravity? Because of, okay, we're going to pivot just a little bit. We're going to talk about roller coasters in a second just to see how many G-forces we got. but it's like, ooh, experiment. So it's the same reason. I need to bring Big Kevin back here. This is going to be fun. Where's Big Kevin? Where's Big Kevin? Okay, baby Kevin's going away. Here's Big Kevin. Okay. So I've got my water here, right? So we're going to learn, stay hydrated. So just like the roller coaster, when it goes up and people don't fall out. See my cup? See, there's water, right? You can see that. Well, watch this. All right. So the water didn't fall out of the cup because there was acceleration of the water backwards into the cup. So as I was spinning it around, okay, I didn't spin it fast enough, a little bit came out. The water is going outward, just like the roller coaster is when you spin it around, it wants to go outward. So if you're going fast enough, you get sucked into your seat as you're going upside down and you don't fall out. Unless you don't go fast enough and you spill some water all over the floor where you're standing while you're trying to teach about space. Okay, back to baby Kevin coming in here. Good question, Wes. So we got these forces, right? This acceleration, because we're trying to figure out how fast can we go in space. So when we're talking about G's, so G's, so that's the force of gravity, right? We got that from up above. Force of gravity. So that's this, right? So the G force is the force of gravity. Now, the force of gravity, right, we can feel it's getting sucked back into your seat like in the roller coaster, right? So that means your body, as you're trying to go fast, you get pushed, right? Well, we can break, right? You maybe have broken a bone. I broke my foot. The camera's too high, but I broke my foot, right? So our bodies can break. Unfortunately, we're not invincible. Bad things can happen if, like, we get hit, right? And if you're going so fast, you got all of those, the G forces coming on you can squish your body, right? So that's bad. So that means we can't accelerate or go super fast really quick because we could hurt ourselves. So that means we got to go slowly to go fast. I see Glenn's got a question. Would a person feel the force of speed if there is no gravity? So here's the thing, is you don't feel speed ever. You feel acceleration. So think of it you're in a car, right? And you're driving on the freeway. Do you feel like if you close your eyes, can you feel that you're going 65 miles an hour or 70 miles an hour? Or if you're flying in a plane, close your eyes, it feels like you're not moving, right? But if the plane or the car speeds up or slows down, then you feel it. So you don't feel speed. So those astronauts that are traveling at the 17,500 miles an hour, they don't feel like they're moving, like they're floating around in space, but you don't feel the wind. So unless you are in a car, you roll in the window, stick your head out like a dog, like Titan was doing yesterday. Titan loves to stick his head out of the window. He's sleeping right now, so we gotta be quiet. Now, he'll wake up, he'll come join us at some point. But then you can feel the wind coming on you. But if you're enclosed in something, you don't feel the speed. Good question, Glenn. Good question. And Karem, you laughed at the roller coaster response, or maybe because I spilled my water. All right, back to these G forces. So roller coasters, right? How many G forces does a roller coaster have? So how many times the force of gravity are you experiencing when you're on a roller coaster? Depends. Like some of them there's like the kid roller coasters and there's like the really intense roller coasters. So it's anywhere between 3 to 4 Gs. So it's the force you feel, 3 to 4 forces of like Earth, gravity pushing on you when you start or when you go upside down on that roller coaster, you do a giant drop, right? That's where you're feeling it. So it's for a very short amount of time, right? So let's write that too. So this is short time. Something just fell outside. Uh-oh. We'll check that after class. So if you heard a big thud, that's what's going on. Something out there. All right. So roller coasters, right? What about rocket launches? Write that down. So, right? So a rocket launch, because we're actually going into space. So the astronauts that we watched go into space on Saturday, what did they feel? Well, they only felt, I say only 3 Gs. Right, so the astronauts, they felt 3 Gs, but this was for a longer period of time. So longer, and by longer, that's about like 8 minutes, right? So that's about how long it takes into space. With the rocket launches, here, takes about 8 minutes, so you're experiencing like those 3 Gs getting pushed back as you're launching for about 8 minutes, okay? So that's what we got there. Now, the typical person, so like what happens, right? If you have too many pushes on you, you can break, right? But before you break, you pass out, meaning like you lose consciousness, like the blood runs away from your head and like pools in your feet, and then you pass out or you faint, right? Now, what's that going to take? Because if we got roller coasters, we can go to 3 to 4 Gs, right? Some people have passed out on roller coasters, right? That's possible. But what we say the typical person can experience up to 5 Gs before passing out. Okay, so some of those like intense roller coasters, some people, they clonk out because their body can't take it. So we're learning all about what the body can take to figure out how fast we can go in space. All right, we just need to learn what the acceleration is. So how quickly can we start to go fast, and then that will let us know of how fast we can go, because it takes time to build up speed. Okay, now let's talk about something that's crazy G-forces, fighter jets. So pilots in these fighter jets, right, because they're going everywhere, all over the place like crazy. So they're making really tight turns, like a super roller coaster in the sky. How many G-forces do you think, stuff's falling off, the typical pilot of a fighter jet has? Take your guesses. I'm going to tell you. I'm going to write it down. Just got to put my fighter jet back. Okay, so the fighter jet. So the pilots in a fighter jet, if you're passing out at 5 Gs, what do you think those are? Well, those are actually, they can go up to 9 Gs. That's almost double, right? Well, it's not all the time. It's short term. You're doing those big turns, or maybe you're accelerating to go really fast to chase like an enemy plane that you want to take care of. Now, we've got a way to help out, so we train for that. We train our fighter pilots to get their human bodies ready, just like we train the astronauts to be able to experience that G-force as they're sitting here waiting to go into outer space. But they also wear something else. They wear something called G-suits. So G-suits, it's like a suit you wear, kind of like, think of it as wearing a life jacket for your whole body, right? A life jacket, like you put air in, right? If you ever had one, and they kind of squish you a little bit. So they have that for the legs, for the torso, which is this part here, and then for like the upper body. And what they do is it kind of squeezes you a little bit so that the blood doesn't pool in your legs. So if you squeeze the legs, then the blood can't go down there, so it stays up in your head so that you don't pass out. So you can wear special pieces of clothing to make sure that you can fly the plane without essentially falling asleep, because that'd be really, really bad. So 9 Gs. Now, the most ever, right, that we've experienced. So there's a couple different sources out there. Well, here's what I found. So for most Gs for a human, there was one that said it was like super, super high. I'm not exactly sure on the sources of that one, but at least this one, someone experienced 46 Gs, but it was only for a couple just seconds, right? Just a couple seconds, all right? Oh, that says, there we go. Couple seconds is what they experienced that we're feeling there. Now, we have, when would humans die, approximately, right? Because we can be squished, right? So I'm just going to call it death. It's a scary word, but death is at around 65 Gs. So that's a sad face. We've even given it a couple tears. Okay, so we're sad. So I've got a question. So G is true gravity, right? So this is from Darshan. So when you're in free fall, it's 0, and when you're standing upright, it's basically 1G. Yes. So when you're free falling, like you're jumping out of an airplane, you feel the force of gravity pulling you down, but there's nothing pushing back against you. Here, we're standing on Earth. Earth is pushing back against us, so we feel 1G as we're here around, just walking, standing here on Earth. So if we can get up to 65 Gs, that's bad. That's where humans, they don't work. So it takes time to build up this speed in space safely. So we experience the 3 Gs as we jump out, and by jump I mean we light the rocket. It's a big bomb with a controlled explosion. It goes this way, and then we get into space, right? And we got more, and we're going that speed. So it's that acceleration we feel till we get into space, and then we're going the 17,500 miles an hour, and we don't really feel it unless we want to go faster and change. So what is the most that we've done? So actually, before I erase this, we got to use blue. So what's the human speed record, right? So we want to know how fast human speed record. So how fast can we go in space? Because our robots can go faster, but humans, we have to be cautious, right? Because we're more fragile and we can break. So the human speed record comes from the Apollo 10 mission. So Apollo, remember? So Apollo 11 landed on the moon, but Apollo 10 went first in this rocket here, the Saturn V. They didn't land on the moon, but they went and orbited around the moon twice. And then once they left the moon and started to come back, they went super fast. Okay? So they went 40,000, and you know me, it's metric, kilometers per hour. So that is the human speed record. Fastest, there's 3 people. 3 people were inside the Apollo 10 capsule, which was this. So this in space was going 40,000 kilometers an hour. Now that's super fast, right? That's our speed record for humans. All right, so we can go faster. We just have to take the time to build up to a faster speed. Now we haven't been back to the moon since the 70s. So it was just over 50 years ago, almost 51 years ago that we landed on the moon for the first time. Then we went a few times, but then we haven't gone back since. So no humans have experienced that kind of speed in 45 years, in like 40 some years. So we're going to bring in humans back to the moon and to Mars, right? And to go to Mars, we're going to need to go faster than this 40 kilometers, 40,000 kilometers per hour. So I'm going to erase some of this because I want to tell you write down a few more things. So we're going to keep that human speed record on the bottom, right? But there is a speed limit in space. There is a speed limit, right? So speed limit in space. Oh, that's too high, too high. I got more whiteboard than I got camera space. So the speed limit. So there's a speed limit in space, all right? And that's the speed of light. So that's 300,000 kilometers per second. You know I like my metric, but I'll give you your imperial. So that's 186,000 miles per second. That's fast. Like, I gotta take a step back because that's so fast. Okay? Light can go that fast in outer space. So that's how the sunlight reaches us in 8 minutes. That's how it's traveling. That's how fast it's traveling. In other stars, so when we're looking in the night sky, that light is traveling to Earth at that speed, the 300,000 kilometers per second. So that's the fastest that anything can go, meaning light, right? But what about us? How fast can we go? So there's this equation. E equals mc squared. And you're like, Kevin, I'm only in like second grade. What is that? So all this is saying energy. You need a certain amount of energy to make your mass, or let's say your thing. So everything has mass, right? To make your thing go fast. That's what it's saying. So you need to put energy, which is why we use propulsion. We need fuel in our cars and our rockets to go fast, right? So you need energy to make your thing go fast. So c is the speed of light. And what that's saying is the closer you want to get to going the speed of light, the more energy you need. So we need ways that can give us a whole lot of energy, like energy from the sun, energy from chemical rockets, energy from wind or from water, from turbines. All those things generate energy, which is why we got lights on. That's energy. So energy makes things go fast. But because we need so much energy, that means we got to figure out ways to make things go that fast. So what do we have so far? So the fastest thing ever right now that humans have built is this. So this is the Solar Parker probe. The Solar Parker probe. Whoa, I'm saying that wrong. It's the Parker Solar Probe. I got a couple words mixed up here. Parker Solar Probe. Sorry about that. Oh, I'm spelling it wrong again. I'm all over the place. So we're just going to call it Parker. Okay. Nickname Parker, named after a scientist. So the Parker Solar Probe, how fast is that thing going to go? It's in space right now. It's going to touch the surface of the sun. It's going all the way to the surface of the sun. So how fast is it going? Well, it's going crazy fast. So we're going to start with the metric units, right? 692,000 kilometers per hour, or for all of you liking miles, 430,000 miles per hour. Now that's the fastest thing that we've got going on in space right now that we've built. Faster than the Voyagers, which are those twin spacecrafts that are outside of Pluto, way out in the solar system, and then also faster than Juno, a spacecraft that's out around Jupiter, which right here, that's the new Jupiter I got behind me. So the Parker Solar Probe, that's the fastest thing out there, right? That is 17 times faster than Apollo. 17 times faster than Apollo. Okay, that's a whole lot faster because we don't have to worry about humans. We don't have to worry about crushing ourselves or bringing oxygen or food when we're working on missions like that. And we don't want to send humans that close to the sun because we're just going to melt, right? Bad news bears. Okay. Now Matt was asking a couple questions, right? What about warp drive, light speed, the Millennium Falcon, make the Kessel Run in 12 parsecs? What's going on with all that? So warp speed, speed of light, warp speed. So let's start with warp speed. Okay. So warp speed. Oh, too many things. So right there. So this is from Star Trek. If you're unfamiliar with Star Trek, this is what Matt loved. So that is, I believe, the Starship Enterprise. If I've got the right one, there's a couple different versions, different spaceships. So the Star Trek Enterprise. So it is said that we're going to call it the Star Trek. That warp drive, Star Trek warp drive. Is this possible? It says that the Star Trek warp drive is 6.5 billion. 6.5 billion what? Kilometers per second. Wow. Kevin, you're telling me that's 21,000 times the speed of light. 21,000 times the speed of light. Okay, that's just not possible. We can't do that because the speed of light is our speed limit. We got it up here. Speed of light, speed limit. The warp drive in Star Trek's just not real. We can't make that happen. So, sorry, Matt, no, warp drive isn't real. Now, light speed is real for light or other little particles, but for humans, light speed is not. It's not possible. So we talk about, what else? Where is it? Millennium Falcon, there it is. It's like, what's the next one? So we got the Millennium Falcon. So, I got one here. I got mine here. But there's a better picture above so you can see that. So Millennium Falcon, it's supposed to be going super fast. So is it real? Is the Millennium Falcon real? Falcon. So Millennium Falcon, according to the websites that I found, it says that it is going, or it can go 25,000 what? Light years in one day. 25,000 light years in one day. Well, that's not possible because the speed of light is going 1 light year in 1 year. So to go 25,000 light years in one day, that's just crazy. So no, the Millennium Falcon with hyperspeed, light speed, that's not possible either. Dang. Because if it were, we could be going super crazy fast places, right? Okay. Now, Matt did ask this thing. It's like, can the Millennium Falcon make the Kessel Run in 12 parsecs? So 12 parsecs, so I need to make this thing go away. Because parsec is not speed. So a parsec, you can see that up over here in the left. A parsec is actually distance. So it's 31 trillion kilometers or 19 trillion miles. We got a little whoop. So what Han Solo was saying when he's like, you know, I can make the Kessel Run with the Millennium Falcon in 12 parsecs, means he took a shortcut. It's not that he was going super fast, it's that he took a shortcut, because it's supposed to be 18 parsecs. But he's like, oh, I can do it in 12 parsecs, which means he's cheating. He's cheating. He's taking a shortcut somewhere. So that's what that means, Matt. Okay? So, unfortunately, no. Now, let's bring it back to reality, right? Like, how fast could we actually go? And I'm going a little bit long here, so this is right here at the end. Just having fun talking about space. So we got the human space record, all of this. So let's get rid of this stuff. Make that parsec go away. So we got the speed of light. So, in the future, what can we do? Well, we could possibly go 10% the speed of light. We're just going to abbreviate it like that. So how fast is that? Well, that's 100 million kilometers per hour, or 62 million miles per hour. Okay, so that is super fast. So theoretically, in the future, we can make that happen. So if we want to go to, as Matt said, other galaxies, Andromeda is our Andromeda. I think I spelled that right. Andromeda is our closest galaxy. Okay, and it's 2.5 million. How far? Million light years. What? So if we were traveling at the speed of light, it would take us 2.5 million years to get there. All right. So if we're traveling at 10% the speed of light, 10% SOL, it's going to take us a very, very long time. It's going to take us more than 2.5 million years. So, nope, not possible. So the last thing that I'm going to leave us with is how it could be possible. I'm looking for something. All right, here we go. And don't worry, Big Kevin's coming back. So let's get rid of. Okay, so how could it be possible for us to make these crazy travel distances? So right here. So if we're here, whoop, right, and we want to go to a place that's over here. Okay, so here's us. Here's the Andromeda Galaxy. It's going to take us 2.5 million years traveling at the speed of light to do that. But how could we do that quicker? Well, we can maybe, just maybe, and this is how like the Millennium Falcon and other places might do this, is bending space-time. So what that means is you bend it, space-time, you can warp things around you, hence warp drive, and then pow, you're there. You see? You can bend space-time, and then you could jump to those places, like jumping into hyperspeed or going into warp drive by warping space-time. Okay? So, yeah, we're decoding Star Wars, Glenn. We got to find that wormhole. We got to figure out a way to have enough energy to figure out how we could like bend or warp space-time. All right, so the future of space, the future of speed in space, is we could maybe go about 10% the speed of light, 100 million kilometers an hour. The warp drive, warp speed, hyperspeed, not physically possible with anything we know of right now, unless we're able to bend space-time and jump from places all over the solar system to other galaxies and other places in our universe. So that's the future of speed in space. Tons of stuff. It really is limited by, for humans, how fast we can accelerate by the G-forces, the push that we feel. And then once we get up there, we can go 100,000 million kilometers an hour, which is going to take a very, very long time to build up to that speed. That's pretty crazy. All right. So Matt Iseman, his social links are below. So if you want to follow him on like Twitter, Instagram, Facebook, check him out. Those are down below. Click the thumbs up if you liked this episode of A Place Called Space. Yeah, we had a lot of numbers and whiteboarding going on today. Hopefully you enjoyed it. Click the subscribe button down below if you haven't done that yet. And I have an announcement to make. So we got Thursdays today, we got the weekend coming up, and then we are only going to have two more episodes of A Place Called Space. Next Tuesday and Thursday will be our last two episodes because schools are coming to a close. We're starting to enter summer vacation, and I want to start putting together some smaller, shorter videos for you, and then they don't have to be live. So I'm going to start working on that after we finish classes next week, but don't worry, we are going to be going out with a bang. Wink, wink, if you can come up with the topic for our last episode. It's going to be something about going out with a bang. All right, and in the meantime, have a great weekend. I'll see you here on Tuesday for our second to last episode. And remember,